I just wanted to say thank you very much, Pierre, for teaching us how to use your software XMapTools. So you are an earth scientist working as assistant professor at the Institute of Geological Science of the University of Bern in Switzerland, and you're also the leader of the group of computational petrology and geochemistry. And that's why one of your specialties is to build this program for analytical geochemistry. And so we are very pleased to listen to this talk today. So thank you very much, Pierre.
Thank you very much. No, it's a great pleasure to show you what I have been doing with this program for the past few years now. And so I want to give you a quick introduction. The idea is just to go across a few concepts that we are using and to show you a bit the evolution of the program and where we are going. When I start presenting XMapTools, the approach, the idea of using compositional maps to try to understand the rock forming processes. I'm a metamorphic petrologist by training and I'm passionate about metamorphism. So, of course, it's terrestrial metamorphism, a bit slightly different than your interest, but we are looking also at minerals, mostly minerals. And when I look at metamorphic rocks, this is an example from Greece. This is a blue schist from Greece. And just on the optical image, you can already see big minerals, small minerals, different colors, probably corresponding to different compositions. And those rocks are quite complex to study because from this optical image, you cannot get as much information as what you would like. So if I now just move from the optical view to the chemical view, this is an iron map, a distribution of iron oxide. It's a quantitative map. I don't give you a scale here, but basically blue means lower iron content, red higher iron content. And what you see is that now you recognize better the minerals, which are rich in iron. You see compositional zoning at different scales, small scale for the small minerals, large scale for the biggest one. And you see that you have patterns that are repeated across the area. So you can start to think about groups and when those minerals formed and how was the chemistry evolving in that rock. And this is why I'm using compositional maps, and that's why I have been pushing this technique now for some years. And when I want to present it, I always start with the conclusions. I have three main conclusions, and I'm going to go through them now. And the first one is that, in my opinion, compositional mapping, if it's quantitative, so this quantitative compositional mapping is always faster, cheaper, and more precise than using single spot analysis. And I hope I will convince you today that this is the case. And if we simply look at a simple example we gave in a paper in 2019. This is the paper on the calibration of the map. I'll come back to the method we use. And the idea was to show that if we look at a composition, this is the first column in this table. It's a composition of a garnet in oxide weight percent. So those are elements here, but we are looking at oxide. If I look at the X-ray intensity of an individual pixel of this garnet with this composition, those are the counts, the number of counts that are collected for the different elements for 1 pixel of garnet. And from that, you can use counting statistics to calculate an uncertainty. And this is the uncertainty in percent at 2 sigma for that pixel. And what you realize is that the number is pretty high. It goes from 2% to 36%. And this is because, of course, I'm looking at one single pixels with low count rates. Now, when you are looking at an image like the one I showed you before, your brain is doing like a gymnastic and is not looking at the value of individual pixels, but it's grouping pixels together. So you are looking at integration of pixels. And if we just integrate now, let's say a window of 10 by 10 pixels together, it means that the X-ray intensity will increase significantly and the precision, so the uncertainty here, will be reduced significantly in percent. And now if I go to 20 by 20 pixels uncertainty, you see that again, you reduce this, you get a better analysis or a better precision in this case. And so by integrating pixels, what we do is like if we virtually increase the counting time, and at the end, we can clearly go above the precision of the spot analysis. And this is what this figure is showing you. On the x-axis, you have the number of pixels that we integrate together. Remember in the case before, I said 10 by 10, that would be about 100 pixels. That would be here on the figure. And on the y-axis, I showed you the intensity of the map divided by the intensity of a spot analysis for 20 seconds on peak, 10 seconds on each background, and so on. The conditions are shown at the top. So basically, if we have a value of 1, and this is the dashed line, it means that we would have as many counts in the map as in the spot analysis. So if I have 100 pixels, or let's say 80 pixels, I will have for a 50 millisecond dwell time on the mapping. If I take 80 pixels, I will be exactly at the same intensity as for a single spot measurement. So everything above that line is result in a mapping procedure that is more precise than for the spot analysis. And we have done that for electron microprobe, and we have done that now also for laser ICP-MS mapping, and it's exactly the same idea. If you integrate pixels and you map with the laser and you collect trace elements maps now, you can now calibrate them in XMapTools as well. And the volume that you analyze over a surface, if you integrate pixels together, will be superior to a volume of a single spot analysis. So this means that, again, you can have a more precise information by using maps than using spot analysis. Okay, the second point of my conclusion is that this method can be now easily applied to major element, minor element, and trace elements. And of course, for electron microprobe, we are mostly interested in major and minor elements, and that was the original development of XMapTools. And in the past 3 years, we have really expanded the technique to push it forward to be able to handle laser ICP-MS maps. And now we can do quantitative compositional mapping on an area that we scan with the laser, and we do exactly the same technique. And you can calibrate all the pixels in your image. The last point of the conclusion is that if you want to apply this quantitative compositional mapping, then you need dedicated software solutions to handle the data, because by contrast to the spot analysis, you will get a much bigger data set. And this is an example. On the left side, you see a composition map of a garnet. Now it's the different elements. You see the elements in the title, it's changing. It shows you the zoning of this mineral. It's quite big grained, millimeter size garnet. And we are looking at the composition in atom per formula unit. So this is after the structural formula calculation. And so you can take all those pixels. For each individual pixels, you have a full quantitative analysis. You can plot this data in a chemical diagram. Here, for example, magnesium in atom per formula unit versus calcium. We can do a density of this diagram to see where we have the different compositions. And what was very important for me is that from this chemical diagram, you should be able to come back to the map and to say, okay, if I want to know where are the pixels that show this range of composition, you can easily do it. And that's where you need to have this kind of the software solution. And this was one of the first tasks that XMapTools was able to do. And so this is why I developed XMapTools, basically. It's now widely distributed in the community. It's quite used in metamorphic petrology, now even beyond metamorphic petrology. And the interest you had in the program is very nice for me, because it shows that the program can be useful even for other people. I kept the program free, and it's now fully open source, which means the source code is available and can be modified. It's widely compatible in terms of data. You can really use the program with a large variety of techniques and instruments. Often the complication will be how you import your data in the program. Not everything is compatible, but you can sometimes, most of the time, you can make it compatible yourself if you know how XMapTools works. It was developed for quantitative petrology. It includes module classification algorithms, There is one add-on for thermodynamic modeling. This is really for metamorphic petrology. We can directly run thermodynamic models in XMapTools. And we have also external functions, several external functions, which are available. And one of my selling arguments for my colleagues is that it was made for a petrologist, by a petrologist, and for petrologists. And this is quite different compared to a commercial software. This is just to show you the development. It has been now a more than 10 years project. I started when I was PhD student, and then I released at the end of my thesis XMapTools 1. It evolved over the years. The point here is to show you that it has received about 30 official updates in 10 years, which means I'm maintaining the program. The program is developed on a weekly basis. It evolves continuously, and every 6 months, about 4 to 6 months, I'll release a new public version. This was the first XMapTools, and it was already centered around displaying the maps. And you would find most of the tools were already there, and it has evolved over the years. This is XMapTools 2 in 2014, basically to change a bit the interface, and it evolved until the version 3 in 2019. That was the peak of XMapTools. And then I realized that I couldn't maintain the old interface, and I decided to switch to a new version, and I started from 0 and starting again. And this is XMapTools 4 that is completely rebuilt with a brand new graphical user interface, much more modern data visualization tools. And this is what I will show you today. So it's much easier. We have reduced significantly the processing time. With XMapTools 3, it was about, like, let's say, an hour for me to take some data from the microprobe and get the quantitative maps. And now I reduced that time to about 20 minutes with the new version, 20 to 30 minutes, depending on the complexity of the data set. And also what is very important for you is that now we have binaries for macOS and Windows. So it's no longer a MATLAB based, or it's still a MATLAB based program, but you don't need to have MATLAB installed on your computer to be able to run XMapTools. And this version is fully open source. The source code is now available on GitHub. So this is a summary slides of what has been included in this version of XMapTools. I'm supposed to release very soon the version 4.2, probably in May or June, and it will include even more functionalities. But basically, the important points I already said. You have apps for macOS and Windows. It is fully open source. We have new interaction tools. It's compatible with laser ICP-MS data, electron microprobe and SEM data, and also with microtomography data. So that was a side project. We made XMapTools compatible to handle this 3D microtomography data sets of rocks. It has a lot of functionalities for petrologists, especially for metamorphic petrologists. And it included now also a quite strong component of machine learning. And I'll show you some examples on how this has really made the data reduction procedure much more simpler. And I'm working on developing the training, the help and training material. It has an integrated user guide directly in the program. We have a resources website, and I'm producing now a video tutorial and virtual classes. So I said for petrologists, we have this add-on for thermodynamic modeling, and this is Bing Quantitative. It's a program that allows you to really select an area of your sample and run a thermodynamic model to try to understand the conditions of formation of this specific domain. It's called iterative thermodynamic model. It's quite interesting. It's a bit an hybrid approach between the traditional approaches, and it's quite nice. And I'll also soon release a new version of this Bing Quantitative called version 2 with, again, a redesigned graphical user interface. So it will get the same upgrade as XMapTools, and it should come in version 4.2, so very soon. At the moment, I only have a demo version, which is available. So there is the official website. That's probably where you went when you Googled XMapTools. If you want to download XMapTools from that website, you have to register. Of course, it's free. The idea of having a registration system is to be able to communicate with you in case we discover a problem in the program. And my philosophy has always been that If there is an error, I'll communicate openly on the error, and I will contact you and say, oh, here there was an error for some time. Unfortunately, those things happen. We have the resources website that contains some description of the different parts of the program and tutorials. This is something I'm working on. It takes a lot of time to develop and to build. And this is not completely up to date, but we are getting there. XMapTools is fully available on GitHub. If you go on GitHub, we have an organization GitHub account for XMapTools. And then there are two directories, the public one with the most updated version for the public, that is the stable XMapTools version. And we have a developer a GitHub version where you can access the pre-release versions. And I'll show you that a bit later on. There are the video tutorials and coming soon to YouTube, and I hope I will be able to record that the tutorial I'm giving today and to use it as a basis to have the first course on how to get started with XMapTools for EPMA data. We have also a mailing list. If you want to subscribe to the mailing list, you can easily find it. It's on the main website. In the menu, you can access to the mailing list. You can register, and then you will receive emails. In case we have problems, I'm communicating things from time to time through the mailing list. And if you have questions, this is also a good place to ask and to search for answers. There is one important point for me, that is the citation guidelines, because XMapTools is completely free and is open source, is fully funded at the moment by the University of Bern, part by my ERC project. And for you as a user, the only reward you can offer us is, and that will support clearly the development of the software, is citations and also to share. So I like to have those logos. If you want to use them, we have this. We have some logos. They are accessible on the website, and you can use them as well. So let's have a few slides on the method for EPMA. So today I really focus on XMapTools for EPMA data. And I want to show you what are the main steps, what is the philosophy behind XMapTools, how do we go from the semi-quantitative X-ray maps to fully quantitative compositional maps. And then in the tutorial, I'll show you how we do it practically with the program. But the idea is when you go to microprobe, what is very easy is to collect spot analysis. All microprobe labs in the world, they know very well how to connect a good quality spot analysis. And what you can also do is you can collect those semi-quantitative maps. Here is an example of the silicon K alpha line for X counts. And you have intensity here of silicon between 8,000 counts and about 13,000 counts. And of course, this is related to composition. So there is a link between the intensity, the X-ray intensity, and the composition. Unfortunately, the link is not fully linear because the different minerals have different compositions, and therefore we have matrix effects. And so we cannot directly transform that intensity map into a compositional map. And it's quite dangerous, actually, to do it directly. But you can collect those X-ray maps. The idea is you simply put the sample under the beam, and then you scan, you move the sample below the beam, and you collect the X-ray counts. And for this example, this is 350,000 pixels for 15 elements. And depending on the settings you use of the instrument, it will take between 10 hours and 40 hours to collect this kind of data set. And you see the result is quite impressive. You have already a good resolution. This is an high pressure rocks from Himalaya. And what you see is this fine grain intergrowth is called the symplectite. I'm sure you know about that. And it shows the decompression of the sample. Okay, so the first step in XMapTools is to import those semi-quantitative maps and to create this mask image. So it's an image showing the distribution of the different classes, the different minerals in my case, and in this case, yeah, the different minerals. And this is calculated automatically by XMapTools using a classification approach. It's a classification task. And I'll show you how we handle the classification. So for this classification, what I implemented in the version 4 is a slightly modified version of the random forest algorithm. And I don't know if you are familiar with this machine learning algorithm. And I just want to give you an idea of how the algorithm is working. Basically, you throw in the algorithm a pixel composition. So those are the X-ray intensities. And the algorithm will classify that pixel. So tell you if it's a garnet, if it's a pyroxene, or if it's an amphibole in the case of the eclogite I showed you. And what is done, it's using classification trees. And if we have a single tree, that would be the entry of the tree, and every node will be a decision tree, will be a decision. For example, here, if silicon is greater than, let's say, 8,000 counts, then you go there. And then if aluminum is lower than 2,000 counts, you go there, and this would be a mineral, for example, quartz. So the tree is automatically optimized by the algorithm, and basically it gives you a path, and you can give all the pixels, and it will give you minerals at the end of the branch. And the idea of the random forest algorithm is instead of using one single tree, you will use a lot of trees. And it will produce different output. It can be all the same, or it can be slightly different. And in this case, the algorithm will just apply a majority voting to determine the final class. So you put the pixel composition, and it determines for you the mineral. And I'll show you how we train the algorithm to do the task we want. So the philosophy of XMapTools is that you control how you train the algorithm to be able to do the task you want. I'll show you this. So when you get this mask image, the idea is now we want to be able to quantify, so to go from the X-ray counts into a weight percent. And this is the calibration approach. And XMapTools is using a very simple approach for calibration. And that, as I told you, what you know how to do in every microprobe lab is to collect spot analysis. So the technique we have is that we collect spot analysis on this area, and then the X-ray maps on the same area. And we can use the spot analysis in each of the different phases to calibrate the maps. And the maps of each mineral will be calibrated independently in order to take into account the matrix effect I was mentioning at the beginning. So how does that work? I'm giving you another example. Here on the left, you see an image. This is an intensity image for manganese K alpha. It's expressed in counts. It's corrected for dead time. And you see the intensity again ranging between about a few hundred counts to a few thousand counts in red. On top of the image, I superpose some spot analysis that we collected in this garnet. Those are the white dots. And you see that we collected spots over the different zones from core to rim, sometimes using a profile, sometimes using just a single spot distributed in the grain. So now, if you take the intensity of the map of all pixels underneath the spot, and you plot it against, so this is the manganese counts, so of the pixels, and if you plot that against the composition in manganese oxide of the spot analysis, that would be the x-axis on that figure, this is the type of graph that you obtain. What you obtain is for every spot analysis, you have a corresponding intensity, and you see that they all line along this line, which means that you have a very simple calibration curve. And if you know this calibration curve, you can now convert all the intensities of your map into of manganese into manganese oxide expressed in weight percent. And this is what we call a map calibration using internal standards. And basically the spot analysis are used in this case as internal standards. And that's all. Once you have done that and you obtain this kind of image that is fully quantified, now we have again 350,000 pixels. Now they are all quantitative analysis. So this is the equivalent of having measured 350,000 spot analysis on this area. And then you can simply calculate, for example, the structural formula of clinopyroxene. And here I'm simply showing you one example. This is the sodium expressed in atom per formula unit. That would be related in our case to the pressure conditions at which the clinopyroxene formed. We have these high pressure minerals, and then we have this destabilization into the symplectite with lower pressure conditions. And this data processing should take you about 1 hour to go from the raw data as they come out from the instrument and to do all the steps, the classification, the calibration, and the calculation of structural formulas. And we even integrated for metamorphic petrologies, we have even tools to calculate from those composition pressure and temperature conditions. But those are really restricted to metamorphic petrology. But we can also add new functions. So if you have something you want to calculate and the program cannot do it, then this is something we can implement, and you just need to contact me in this case. Okay, so those were my conclusions for this introduction, that compositional mapping is faster, cheaper, and more precise than spot analysis. It can be applied quite easily to major, minor, and trace elements, but you need software solutions, and that's why I've been working on developing XMapTools in the past years.